cross stuff out if you need to.
Do I have markers? That's the question.
There are markers here.
Oh, man. I might do that.
And an eraser.
Yeah, yeah. Totally my choice. Kenny G? No.
A couple more minutes, right? Yeah. Just hold your hand up when you're ready. Then you face music, do what I have to do with my reports, and then we go right into it.
Hello, everybody. Can you hear me? And welcome back, those of you on the live stream. This is leveraging the HPCC Spark ecosystem. So if you're not in the right place, please proceed to where you should be. I want to take this time to introduce to you James McMullan. He is a developer on the HPCC platform, working on the Spark HPCC ecosystem and connectors. Today he's going to talk about some of the work he's been continuing related to that particular connector. He's also going to introduce Zeppelin, what it is and how to use it, and he's going to talk about using random forests to do exploratory data analysis and build a predictive model. So please hold your questions until the end, and we'll have a question and answer session. So James, go ahead.
All right, good afternoon, everybody, and thank you, Ken. So as Ken mentioned, I'm James McMullan, and today I'm going to be talking to you about some of the work that we've been doing with Spark and HPCC. And in particular, last year we kind of announced this integration, this connection between Spark and HPCC that we've been working on. But last year I just kind of showed you like, oh, we can read and write data, but I didn't do anything with it. So this year I wanted to do something a little bit more. So during the presentation, we're also going to be building a random forest model using data from HPCC. All right, so let's get started. So before I really kind of jump into all of that, I want to give you a quick overview of how the talk is kind of broken down here. So to begin with, I want to talk a little bit about the Spark HPCC plugin and connector. And basically, I'm going to be talking to you about how to do the basics of reading and writing, giving you some code examples. And if you saw last year's talk, there's not going to be a lot that's new here. We have been making some improvements, but from the outside, most of this stuff is going to be pretty familiar. I'm also going to briefly introduce Apache Zeppelin. Apache Zeppelin is a multi-user notebook environment, and this is something we've been using internally to do data science. And so I'm going to be talking about that, and the reason I'm going to be talking about that is because I'm going to be doing the demo in Apache Zeppelin itself. So I'll give you a brief introduction to that as well. And of course, we're going to be creating a random forest, so I want to give a brief introduction to random forest so that you have some background on random forest when we start. I'll also be using a data set from Kaggle. If you're not familiar with Kaggle, it's an open source competition website for data scientists. So you can go there, you can compete in data science competitions to win prize money. And again, at the very end, we're going to be talking about where we're going to be moving forward with the Spark-HPC connector and the ecosystem, and then finally some closing thoughts. All right, so to begin with, let's talk about the Spark-HPC Systems connector. So there are two main parts to the Spark-HPCC integration. The first one is the Spark-HPC Systems connector, and it's really a library for Spark. It's written in Java, and it allows us to read and write data from HPCC and write it back to HPCC as well. It can be installed in any Spark cluster, so it doesn't necessarily have to be a Spark cluster that we manage, and I'll be talking about that in a second. It can be any cluster. So we also have the Spark plugin, which is a managed Spark cluster that gets installed alongside your HPCC cluster. And it mirrors the Thor cluster that you install it on. So if you have a 200-way Thor cluster and you install the Spark plugin, you're going to get a 200-way Spark cluster as well, standing alongside it. And the great thing is you don't have to worry about all the complex configuration options that are kind of in Spark. There are a couple of small things, kind of gotchas that we have learned over the time that we've kind of built into this. So you don't have to figure that out. You don't have to handle that configuration yourself. We're handling those more complex options for you. And again, if you're familiar with HPCC and the config manager, you can do the Spark configuration through config manager as well. And again, the Spark plugin is automatically going to install the Spark HPCC connector. That way you can read and write data from the get-go. So if you want to get started with this, it's as simple as going to the HPC Systems website, downloading that Spark plugin, and installing it. And again, as soon as you start up HPCC, you're going to get a Spark cluster running alongside it. So it's pretty kind of a high-level overview of how all this stuff works. But the important thing is you can get Spark installed and running, and you can run with it. All right, so the progress since last year. In HPC 7.2, we added remote writing support. So before we were only doing writing only co-located from the Spark cluster to the Thor cluster, or HPCC cluster. So in 7.2, you can run out write to remote clusters as well. We've also been improving the performance, especially in Python and R. So last year, we were reading data in Scala and Java. We'd have to serialize it to the Python and R runtimes, and then deserialize it on the other side. And that's a pretty high performance bottleneck. So we were able to remove that, and that's about a 3 to 4x performance improvement for Python and R. So now we're at a uniform performance across Scala, Python, and R. And we've also been doing a lot of testing internally. We've had data science teams using this system, so we've been using it quite a lot, finding bugs, increasing reliability, that sort of thing. So it's a lot more stable than it was last year when we first announced it. And of course, we've introduced Data Source API v1, which is where a lot of that performance came from. And it also gives us a unified read-write interface. So if you're familiar with Spark at all, this is going to seem really familiar. And the examples I'm going to give are using that Data Source API interface. All right, so moving right along. So this is reading, and this is, again, the Data Source API v1. And we have a Python PySpark example and a R Spark R example. And you can see that they're really similar. And this is what I was talking about by a unified API. In the past, we had very different interfaces for each language. Now they're nearly the exact same. So to start at the top here, we basically got our cluster URL. And this is actually my local virtual machine, which the demo you're about to see is all done on my local virtual machine. So that's my local virtual machine. And basically, this is the same URL that you get for ECL Watch. And then I'm reading a file, this example data set, so that's my file name. And then to read a data frame, so the DF is our data frame, we're saying Spark read load format HPCC, that's just making sure that it's going to read our code, right, run our code. We're going to give it our cluster URL for our host, username and password. These two are important. I'll get back to that in a little bit further in the presentation. And then we have a couple of new things this year. So limit per file part's pretty interesting. What this is doing, it does exactly what it sounds like. We're going to be limiting the number of records that we read in per file part. So if you have a 200-way Thor cluster, or a 200-way Thor cluster, and you have 200 file parts, this means that we're going to get 100 records from each file part. So you'd have 20,000 records. And this is really interesting if you want to read in a large data set. Let's say it's in terabytes and has billions of records. You don't want to maybe pull all that in at the beginning when you're just doing data exploration. So this allows you to pull in a small subset of that data. And it's very performant. You basically get the same I/O for 100 records that you would get for 20,000 records in this case. The next interesting option we have here is project list. And here you can kind of define the fields that you want to read in. So a lot of data sets that we have hundreds of columns. And you may only want 5 to 10 of those columns when you're doing a data analysis. So you can provide the list of columns that you want. This is comma separated and period delimited. So you could say field 1 dot child field to get child field well. And then again, file access timeouts and path. That was the same as last year. And again, Python and R are very, very similar. All right, so the right side looks very similar again. So we're taking our data frame from the last slide that we read in. So we're reading into this data frame. And then on writing, we're saying take our data frame, df.write save. Again, we're saving back to HPCC. Mode is a little bit different. If you leave this off, you get an error if you try to overwrite a file. Otherwise, you have to specify overwrite. It's pretty straightforward. The only other option that's maybe of note is cluster here. So here we're saying my Thor. So if you have a HPCC cluster that has a number of Thor clusters running on it, some of ours have 6 Thor clusters, right? You would specify the cluster group name there. And that's pretty straightforward. Again, Python and R are the same. And again, this interface is basically the exact same in Java and Scala as well. All right, so Apache Zeppelin. So again, Apache Zeppelin is a multi-user notebook environment. And this really solves a problem for us that we had. When we first started working with Spark, we realized that asking data scientists to open up the command line and submit a job via command line is not a good way to go about this. And so in HPCC, we already have some functionality to do this automatically for us. It's part of the ecosystem. In Spark, it's not. So Apache Zeppelin solves that for us and gives us a front end for submitting Spark jobs. And it's collaborative, so you can have multiple people in the same notebook working together. It has version control, et cetera, built in. And if you are familiar with Jupyter Notebooks, it's very similar to Jupyter Notebook, but the difference is it's multi-user by default. So you don't have to go use Jupyter Hub or anything like that. Everyone can work together in the same centralized environment. It also handles things like job queuing and resource allocation for us, which is a big deal. If you have a bunch of people, 30 people using the same environment, you want to make sure that they each have the resources they need. And again, Apache Zeppelin can handle that for us. So that's one of the reasons that we chose to use Apache Zeppelin. Again, I want to point out this is an open source project. It's not something that we're releasing. It's just something that we like and we recommend. And we've also been contributing some code to Apache Zeppelin to solve some issues that we had. All right, so again, multi-user environment by default. It's a significant improvement over Jupyter Notebook. Again, it has version control built into all the notebooks. Interpreters are bound at a paragraph level. This is really fascinating. So in let's say, Jupyter Notebook, if you create a notebook, it's going to be for, let's say, Python. And you can only write Python code in there. But in Zeppelin, you can write Python code, Scala, R. You can use different libraries from all those different languages, and then you can move data between them. And this is really powerful, and I'll kind of show you that during the demo. It also has built-in visualization tools, so if you want to see the contents of a table, you can easily do that. If you want to graph the contents of a table, you can easily do that. Moving data between languages, that's again really important if you're going to have multiple languages in the same notebook. It instantly handles that for us. And credential management is also included. This was kind of a big deal for our security team. If I go back, we don't want passwords in code, right? We don't want that. Our security team really doesn't want that. And so this is one of those things that Zeppelin can help out with, and this is one of the things that we helped contribute to Zeppelin. All right, so with that, so we got a brief introduction to the Spark-HPCC connector, brief introduction to Zeppelin, so let's actually go build a model. So before we do that, I really should talk a little bit about random forests for those of you who aren't familiar with it. So random forests are ensembles of decision trees. And so basically, we're going to have a bunch of decision trees that are working together to answer our question. And so as an example, here's a decision tree over here on the right. And right after we got lunch, I guess this is appropriate. But so basically, we start at the top here and we ask a question, am I hungry? If I am, and I have $25, then I go to a restaurant. If I am hungry and I don't have $25, I go buy a hamburger. I guess a hamburger is cheaper. If I'm not hungry, I go to sleep. This is probably the laziest decision tree ever. A random forest is a bunch of these working together, and there are a bunch of different random forests, and so they should be good in different ways. And what we do is we take the outputs of each random forest and we average those together, and we get a better result from the ensemble than we could with any single decision tree. And that's really important. And this was a little bag of, I can't remember the name of the paper, it's from 1998, I believe. So it's been around for a bit, but it's still a very powerful technique. The one thing to mention is, this decision tree is meant for us, we can interpret it, but for a computer, this would have to be numeric, of course. So one of the things that we're going to be doing when we're creating that model is converting all of our data into numeric types. And so instead of saying, am I hungry, I would say, is my blood sugar less than 0.5? All right, so what model are we going to be building? So I went to Kaggle and found this data set. It's a bulldozer data set that basically tells us how much a bulldozer is worth at auction. And so imagine we're working for a company, let's call it Bulldozers are us, and we're data scientists. And our company, what they do is they buy bulldozers in cash, and then they turn around and sell them at auction at a higher price, right? So we have to make sure that we can build a really good predictive model that predicts this auction price accurately. And so that's what we're going to be doing. And the cool thing about Kaggle, one of the reasons I went and grabbed a data set from Kaggle, is that it's an open source competition. And this data set was from about 6 years ago. So the results are already in. We can go and compare our results to the Kaggle results to know how well we're doing. It's a little bit hard in machine learning to know, how good your model actually is. And so since there's prize money attached to the Kaggle data set, and this is already complete, we can really kind of be sure how good of a job we're doing. One of the other things I want to point out is that the score on the competition is calculated in root mean square log error. And that's a little bit different than your typical root mean square error. Essentially what this is it's a percentage based versus a absolute error. So if we predict our bulldozer price is $100,000 and it turns out to be $110,000, that's a pretty small difference, right? But if we said, it's $20,000 and it turned out to be $10,000, that's still an absolute difference of 10,000, but it's a percentage difference of 50%. It's a pretty big difference. And so that's what root mean square log error is going to give us. So you're going to see me take the log of the sales price when we get started. All right. So due to technical reasons, so that we can do it with a live stream, et cetera, the demo is going to be a video of me going through this, so I'm going to be trying to talk over it. Hopefully it works. If not, I do actually have this running on my laptop, so if you're interested, come find me afterwards and we can go over it again. All right. Hopefully this got started. So this is the actual competition on Kaggle, and you can see these are the top 3 people. These top 3 people actually are in the money, quote unquote. And you can see that the prize money was $10,000, so it's not bad. It's a pretty good incentive for these data scientists to actually do a really good job on this. So again, first place gets $6,500, and so on and so forth. And we can see that these three, 0.22 is the score. So remember that's the top one. I'm sorry, 0.229. That's the top score. And again, this person got almost $7,000 for winning this competition. All right, so again, it's open source data. So there's a training set and a validation set. And the validation set's about 30% of the training set. And so I went ahead and grabbed this and downloaded it and put it in HPCC, and that's what we're looking at here. And you can see that this is all string data. There are about 52 columns, so it's actually a good bit of data. And one of the things I want to point out is we're going to be doing data exploration using machine learning. So I'm not going to be using the data patterns and stuff that the main presentation was talking about. We're going to be trying to use the machine learning to tell us that kind of data that we want. All right, so this is Zeppelin. And again, this is a Zeppelin notebook. You can kind of see we have paragraphs. This is a markdown paragraph. So I can enter markdown there, and I just kind of entered information on the bulldozer model here. All right, closing that back up. All right, so the first thing we're going to do is retrieve our data from HPCC. Again, this is all going to be running in Spark. And so an important thing to note are these credentials right here. And I said before that credential management was kind of important, and you'll see that user.hpcc. So there's a credential manager built into Zeppelin where you can enter credentials. So we see the entity is HPCC, and so where it finds user.hpcc, it's going to inject it at runtime. It won't leak, so if this gets printed out, you won't see it. And this is one of those things that we helped contribute. So this gets our passwords out of our notebooks and make sure that we can actually collaborate. Okay, so we're basically reading the training data set, reading the validation data set, and then I'm going to be doing something here. I say z.put. Z is the Zeppelin context, so anywhere you see that, that's a Zeppelin function. So I'm saying z.put the bulldozer train data set into the Zeppelin context. And this is going to allow me to transfer it between languages. So this was Scala, and this is Python. So I'm transferring it from Scala to Python using z.put, and then going back and getting it again with z.get. And again, I get my data set back out from the Zeppelin context. And then I'm using z.show to show the actual the content of that data set. And if we look through here, there's a kind of a lot of different data types. We can see that this is like categorical data and like dates. We have a number of categories. We also have some integer data sets. So again, decision trees, they have to operate on numeric values. So one of the first things we can do is kind of process our data set, get rid of any null values, convert strings and dates into some sort of numeric value. And of course, we also need to convert our sales price to log of sales price. So to begin with, I want to tackle the date first. And so one of the cool things about Spark is it has built-in SQL support. So you can just write SQL to query, make new tables, et cetera. So one of the first things we're going to do is we're going to register a new SQL function, a SQL UDF, user-defined function, and it's going to be called parse date. And I'm just going to use a Java simple date format. You really don't have to be concerned too much about how this works, but basically I'm creating a new SQL function that I can use later. Something to note is it's better to write those in Scala than, let's say, Python. Scala has a little bit more performance there, and there are some query optimization overheads for Python. All right, so first off, there's some columns that we just don't want. Sales price is one of those things because we're going to convert it from sales price to log of sales price. And sales date is, again, something we're going to convert. And I'm actually going to break that out. We're going to do a little bit of feature engineering. I'm going to break that out into a bunch of different subtypes, year, month, that sort of thing. All right, and we have a bunch of integer columns that we need to convert. And so our string columns are going to be the columns to ignore and the integer columns removed from the total columns. And that's going to give us our string columns. And they're going to build this string indexer using those for each one of those string columns. So there's a for each down here. So for each column in string columns, I'm going to create a string indexer. And the string indexer is going to go through here and say, OK, for hydraulic, we've got 2 valves, standard, et cetera. And we're going to index each one of those. So we're going to get all the unique values and say 2 valves comes up first, number 1. And so that's going to be replaced with a 1. Again, we're just converting these things to numeric values. We can combine all these things into a pipeline. That's what our category transformer is. And then we can run that on our data set, and it's going to do the transformation for us. One thing to note, that handle invalid, that's basically saying if we have a value that we haven't seen before, we want to keep it, and we're going to set it to 0. All right, so we're going to define a Python function here, process for regression. First thing we're going to do is we're going to run our category transformer to turn those string columns into indexed values. And then we're going to drop the old string columns. We don't need them anymore. The new string columns are going to be the original name with underscore index attached to it. And then we're going to name those back just so that it's consistent. All right, next thing we're going to cast our numeric, our values that should be integers into integers and handle any null values that are there. And then finally, we're going to cast our sales price to a log, and we'll call that log of sales price. And so what we're doing here is we're concatenating a bunch of string SQL statements together into one SQL statement that we can run against the data set. All right, this is actually where we're breaking out we're using parse date here, our SQL UDF, our Scala SQL UDF. Yeah. And so we're breaking out year, day of month, day of week, day of year, that sort of thing. And this is just going to make it a little bit easier for the system to analyze. A little bit of feature engineering. Yeah. And then we're going to create a temporary view into this data frame. That's what we're doing here. And then we can actually run our select statement onto this to build a new table. And so df is going to be our new data frame, and we're going to return that. And then we're going to run our function that does this, this processing to turn everything into numeric values here on both our training and validation set. And then just for fun, we don't actually need to do this. We're going to write it back to HPCC. All right. And so this is the data set that we wrote back to HPCC. And you can see it's all numeric values. You can see our log of sales price is now 10 versus 100,000. Right? And so we're going to load this back from HPCC again. Again, we're loading it in Python. Should seem pretty familiar. And then we're going to put it back in the Zeppelin context. We don't need to do this again. And the other thing I want to point out is I'm also persisting this. Persisting in Spark basically means keep this in memory. Don't drop it. Spark will do that if it decides it's better to just go load it back from HPCC. Doing this means that keep it in memory. It's a little bit better for performance. All right, so now we're actually going to train the model. And so we've got our train random forest model function here. And the random forest regressor is the thing that is actually going to be doing the work. But we do have a little bit more to do. So we've got our feature columns and we've got our prediction column, the log of sales price, right? So we need to break those two apart. And so we're going to use a vector assembler to take our feature column and put that into one column called features. And this is going to be a vector of those features. Yeah. A couple things to note. The vector indexer here, I'm skipping down a little bit. We have a max categories of 7. And so what this is going to do is there are going to be a few categories that, a few columns that have a ton of options. So a model for the Bulldozer is an example. This has, I think, 5,000 different values, unique values. And so if we turn that into a category, how random forest worked, it wouldn't be great. So we're going to treat that as a continuous variable. And so, let's see. This is actually where I'm going to look at that. Yeah, so this guy, there are a ton of different values for that. So we're going to treat that as continuous because we specified that we only wanted category variables if they have less than 7 unique values, 7 or less. All right, so that's our max categories. Again, handle invalid, saying keep. If we have run across values we haven't seen before, just set them to 0. All right, the other thing I want to talk about is feature subset strategy. I said that each decision tree in the random forest has to be different, and that's what our feature subset strategy is. We're saying we're going to take, of the 52 columns, we're going to take half of them, 0.5 up here. We're going to take half of those, and we're going to randomly select half for each decision tree. That way they're different in some manner. So that's feature subset strategy. That's a really important piece and something that you would want to tune. It's a hyperparameter. Next is number of trees, and this is kind of telling us how many decision trees we want to build into our random forest. 40 is actually pretty small. For production, you'd want this to be hundreds, it's maybe even thousands, depending upon the setup. Max bins is also interesting. I won't go too much into the detail there, but that's determining how it splits up continuous values. That way it doesn't have to do as much computation. Spark starts this at 32. Scikit-learn does it in 256. I found that 256 is better. Max depth is the depth of the tree. So that first tree that I showed you, that hamburger tree, right? That was only a depth of 3. So a depth of 15 means that we can go a lot deeper. It can be a lot more representative of the data. And this is, again, something you want to tune. To tune that, I just started with 5, 10, 15. I found 15 was better than 20, so I stopped at 15. So we're going to assemble this together into a pipeline. So we've got our assembler and vector indexer, which are taking those feature columns and putting them into a vector, and then taking our log of sales price out and turning that into our label column. And then we're just take our random forest and combine that at the end. And then we're going to take our pipeline and call fit on the training data and return our model. So at the end here, we just get this model. We can say model train random forest on our training data set. And then we can take the model and we can run a transformation on our validation set and get out predictions. All right, so from the predictions, then we can run a regression evaluator, and we can get out the root mean squared error. And again, we already took the log of the sales price, so this is actually going to be RMSLE. It's not going to be the root mean square error. It's going to be the root mean squared log error, which is what we want. All right, so we evaluate all of our predictions, and we get a RMSLE of 0.265, 0.266 actually. All right, so jumping back over to Kaggle here, let's see how well we did. So this is 0.256. I don't know if you can see that. Yeah, so we're in between 59 and 60. So not bad. There are 475 or so entries in this, so we're in the top 11%. And we really haven't done any feature engineering. We haven't really done any data exploration on this, so we can actually do a lot better. So one of the cool things about random forest is they'll tell you if something's important or not. And so that's what we're mapping here. We're taking the feature importances from our random forest. So this is telling us, giving us the column importance, and then we're going to sort this. This is essentially what all this is doing. We're sorting this, and then we're just going to plot it out. And so this is going to tell us which features are the most important. And this visualization is, again, built into Zeppelin. It's pretty nice. Yeah. And again, I'm sorting by importance here. All right, and we can see product size, age, enclosure. Enclosure is fascinating. This is actually whether the Bulldozer has AC or not, which I figure is probably, I guess, pretty important. But we can kind of see this as a long tail. And all that data out there, all those columns, we probably don't need them. They're not that important for the model themselves. We can probably select the top 25 of these guys and rebuild our model, and we get a lot better results. And in fact, if you do that, you do get a lot better results. I'm not going to do that here for time purposes. One of the other things we want to look at is how correlated two columns are. So maybe maybe two columns are really important, but maybe they're encoding the same type of data. And so what we're going to be doing here is we're going to be taking I'm jumping around a lot here. We're going to be taking a Spearman R correlation between all the different columns and determining how correlated these guys are. And then we're going to plot this with a dendrogram. This is a Python library. It's actually matplotlib that's giving us this. And I'm not going to go through this code. I mean, this is available. I'll show you the link at the end. All right, so Spearman R correlation. We're plotting a dendrogram. All right, so over here on the left, the further to the right that these features break apart and split means that they're more correlated. So these guys that are branching off over here, this group is highly uncorrelated to this group. But these guys at the end are highly correlated. And so, in fact, we had to zoom in here to see, they don't even split off until you get to the very far right edge. So these are probably encoding the exact same data. So even though these showed up in the top 25, we can probably drop them, or drop 2 out of the 3. So you do experiments to figure out which ones you should drop, but this kind of tells us that we want these guys and we don't want Scarfire in there. All right. One thing I want to point out, almost all these guys are random forest, and to get down to that 0.22, this is what you would do. You would take a look at your top features, only use those guys, take a look at the correlations between the features, and make a better model. And of course, increase the number of random forest, decision trees in the random forest. And if you do that, I did some experiments, again, a little too long for the presentation, but I was able to get down to like 0.24, 0.23. I think that's it for the video. So again, our RMSLE score is 0.26. It's not bad, right? Especially, this wasn't that much work. If you go look at the code, it looks a little bit more complicated than it is because I was breaking it down in that manner. But it's really not that complicated. And again, we got 50th at about 450, so that's 12%, about 12%. Again, a 0.22 is possible with random forest. If you want to do even better, deep learning can do way better actually. And the winner for that year, that was actually a deep learning model. And that's actually right when deep learning started to pick up, so it was around 2013. So to get down to 0.22, again, we do some more feature engineering, a little bit more hyperparameter tuning, and again, deep learning can do a lot better. All right, so that was kind of an overview of Spark-HPCC, what we've been doing, what you can do with it. My goal here was to kind of not show you how to build a random forest. It was to get you excited about some of the stuff that you can do with Spark and HPCC together. And it's not just machine learning. So as an example, there are a bunch of libraries out there that you can use. Optimus is a good example. It does data cleaning for Spark. So a little bit like data patterns that we have in HPCC, but it can do some other interesting things as well. Matplotlib, that actually created that dendrogram that you saw. Spark streaming, this is really great for IoT events, telematics. Yeah, it solves a lot of hard problems around pulling in streaming data, deduplicating the data, making sure that each event is only added into your data set once and added every time. And then, of course, deep learning with Spark. This is possible now through external libraries. Yahoo, of all people, actually point out one of the libraries for Spark. It hooks up with TensorFlow. In Spark 3.0, we're currently on 2.4. When that's released, TensorFlow will be built in natively. So some closing thoughts here. Spark and HPCC working together, you get a lot of benefits. So you can analyze the different strengths of each platform, choose the best things, and use those. Our goal is to allow you to do more with your data. We are the platform team for HPCC, so we would like you to use HPCC. But again, this integration has some great features. Things like that matplotlib dendrogram. We don't have that, but with Spark you now do, right? Apache Zeppelin is really great. We've been adding code to it. I think this is potentially a game changer for some groups, right? You can collaborate on a notebook. So that notebook I showed, multiple people could be working on that, doing version control, et cetera. One thing I really want to point out is I'm not a machine learning researcher or a deep learning researcher. This isn't what I usually do. But it's really accessible. I started learning this in my spare time earlier this year, and I started using the FastAI online open course. And I was really blown away by how easy it was to get started. If you can write software, you can learn this stuff. You go read these papers and it's a bunch of Greek, right? I've got a background in math and I still don't want to read those papers. But you don't need to know any of that. You don't need to know calculus. Even though this is based in calculus, you don't need to know calculus to get started. You can go do all this stuff if you can program. And so as part of this year's conference, we're saying challenge yourself, right? So I challenge everyone in the room. If you can write software, you can learn about machine learning and deep learning. All right, any questions? And I think Ken's got a microphone, so if you've got a question, raise your hand.
Thanks for the presentation. We in FIDO team use lots of data, and we are looking into bringing in Spark.
Great.
Our dev environment is on 7.2.28 right now,
Okay.
and we have Spark installed in it. So I'm trying to understand, is it possible to bring data out of Thor and make it available in Spark context and have UI applications directly use Spark rather than going that extra hop of make a Spark call, and then Spark calls Thor, and then Thor returns?
That's a great question. So Spark doesn't necessarily have a built-in distributed file system. It uses HDFS,
Right.
which you can call that's the distributed file system. So if you wanted to do that, what you would end up doing is you would pull data out of HPCC and write into HDFS.
Right, but does it have to sit externally? Can it sit within the
We-
context since Spark is already in there?
That's a good question. So we don't have an HDFS cluster set up. That's not what we're installing when we're installing Spark. Maybe something we look at in the future. But at the moment, no. Like they would live in HPCC. And again, it's kind of choosing your distributed file system.
And can it go from Sorry. Since it's decoupled in the Spark environment, your HDFS and your Spark code
Right.
perspective of accessing your data,
Right.
is it possible to go to the OpenStack and then write it to OpenStack and then access it from OpenStack? I mean, have you tried anything in that?
I haven't tried anything like that. If you can figure out a way to get it like from Spark, we get it into Spark for you, right?
Right.
Whatever you can figure out from Spark, you can do, right? So if you could do it normally in Spark, you can do it through the system. Does that answer your question?
Yeah, so then we'll be able to, so we read it once from HPCC through Spark,
Right.
and then write it to OpenStack from Spark,
Yes. Yeah, you could do that.
and then try that. Okay, all right.
Yeah.
I'll keep you guys involved in it.
Yeah, we definitely want more testers. So anyone that's interested in doing this, contact us.
Yes,
Yeah.
I talked to Rodrigo last week about it.
Great.
Yeah, thanks for the presentation. I guess I have two questions. My first one would be, have the Zeppelin notebooks, have you had any experience trying to productionize those?
That's a great question. We are actually in the process of doing that now. We've had a test instance with some data scientists in there and playing around, and we would take it down and things like that, and so it's been a little bit of a headache, but we're in the process of doing that today. Actually, last week it's what we were doing. So yeah, we're in the process of that. We're not done yet.
And I guess the second question is around the completeness of the documentation.
Sorry, say that
How
again?
complete is the documentation for getting it set up, managing it, taking care of it in general?
Yeah, that's a good question. It's probably not as good as it should be. We definitely have documentation. If you go to use the documentation and you get stuck, definitely contact us. But yeah, it's there. It should be good. If it's not, definitely let us know.
Thanks.
But to be clear, we don't document how to deploy.
Yeah, Apache Zeppelin, we don't document or, yeah. I made it. Yeah, we don't document or package Apache Zeppelin. We do use it.
And does it also allow you to do the command line interface without the Zeppelin, if in case I want to do some automation around it and stuff?
That's a good question. Depending on your setup, yes. If you set up Apache Zeppelin to use all of the resources, it's going to take all the resources and manage them itself, which is kind of what you want. But if you did actually set it up so Apache Zeppelin only took half the resources on the Spark cluster, you could still submit jobs via the command line.
Thank you.
All right, any other questions?
Okay, James. Thanks, James. We have a short break. Those of you in live stream will start up again around 2:20. So please make your way to your next session and enjoy the rest of your day.
Thank you.